Hello, in this lecture we'll find out the area of the green shape using two different methods. In the drawing we have two circles. Each circle is passing through the center of the other circle, and we also know that the radius of each circle is equal to 5 units, and we want to find out the area of this green shape. So we'll start with the first method, and first of all I'll explain to you the term sector. Sector is the area inside the circle that is bounded by two radiuses and the arc between those two radiuses. So this green shape is sector AOB, and the area of a sector is equal to the formula for the area of a sector is equal to pi r squared times the angle between the two radiuses over 360 degrees. In this case, the angle between the two radiuses is 60 degrees. Therefore, the area of sector AOB will be equal to pi r squared times 60 degrees over 360 degrees, when r equals to the radius of this circle, and the angle could be any angle, not necessarily 60 degrees, but any other angle. In this case, it equals to 60 degrees. So the area of a sector is equal to pi r squared times the angle between the two radiuses over 360 degrees. Okay, again, a sector is the area inside the circle that is bounded by two radiuses and the arc that is between those two radiuses. And the area of the sector equals to pi r squared times the angle between the two radiuses over 360 degrees. And we also have another term that is segment. Here, segment AB is defined as the area inside the circle that is bounded by a chord and the arc that is attached to that chord. So here, segment AB is the area in the green shape that is bounded by arc AB and chord AB. And the area of segment AB equals to the area of sector AOB minus the area of triangle AOB. Again, the area of sector AB equals to the area of sector AOB minus the area of triangle AOB. Okay? So here we will define the center of this circle as point P, and the center of this circle as point Q. We will define the first intersection point between those two circles as point A, and we will define the second intersection point of those two circles as point B. In the next step, we will join points P and B together by a straight line. Line segment PB is the radius of this circle because of the fact that it starts from the center of the circle, that is to say from point P, and ends at point B, that is a point on this circle itself. Therefore, PB is the radius of this circle, that is to say it equals to 5 units because of the fact that the radius of those two circles are equal to 5 units. We join points Q and B together by a straight line. QB, line segment QB is defined as the radius of this circle because of the fact that it starts from the center of this circle, that is to say from point Q, and ends at point B, that is a point of this circle itself. Therefore QB is the radius of this circle, that is to say it equals to 5 units. Likewise, we join points A and P together by a straight line. AP is the radius of this circle because of the fact that it starts from the center of the circle, that is to say from point P, and ends at point A, that is a point on this circle itself. Therefore AP is the radius of this circle, that is to say it equals to 5 units. We join points A and Q together by a straight line. AQ is the radius of this circle because of the fact that it starts from point Q. Line segment AQ starts from point Q and ends at point A, that is a point on this circle itself. Therefore it is the radius of this circle, that is to say it equals to 5 units. So here we created quadrilateral APBQ, and quadrilateral APBQ is a rhombus. A rhombus is a quadrilateral that all of its sides are equal to each other, but not all of its angles is equal to 90 degrees. So any quadrilateral that all of its sides are equal to each other, but not all of its 4 angles is equal to 90 degrees, it is defined as a rhombus. So I write it down that quadrilateral APBQ is a rhombus. Quadrilateral APBQ is a rhombus. And we join points A and B together by a straight line. Line segment AB is the first diagonal of rhombus APBQ, and we join points P and Q together by a straight line. PQ is the radius of this circle because of the fact that it starts from the center of the circle, that is to say from point P, and ends at point Q, that is a point on this circle itself. Therefore PQ is the radius of this circle, that is to say PQ equals to 5 units. So here we have two diagonals of rhombus APBQ, diagonal AB and diagonal PQ. And the diagonals of a rhombus has two characteristics, so I'll write them down. The characteristics of the diagonals of a rhombus so the diagonals of a rhombus have two characteristics that is relevant to this question. The first characteristics of the diagonals of a rhombus is that they are perpendicular to each other. So here the diagonal AB is perpendicular to PQ, and the diagonal PQ is perpendicular to diagonal AB. First of all, we will define the intersection point between diagonal PQ and diagonal AB is point M. So here AB is perpendicular to PQ and PQ is perpendicular to AB. That is to say, we have here four right angles. And the second characteristic of the diagonals of a rhombus is that they bisect each other. So here diagonal AB bisect diagonal PQ. That is to say, PM equals to MQ. And then diagonal PQ bisect diagonal AB. That is to say, AM equals to MB. AM equals to MB. So we know that PM equals to MQ. So if PM equals to X, then MQ will be also equal to X. And we know that X plus X equals to PQ. X plus X equals to PQ. X plus X is 2X, so 2X equals to PQ. But we have already found out that PQ equals to 5 units. So we write here that PQ equals to 5 units. So from this equation, we will derive that 2x equals to 5. 2x equals to 5. Here we will divide this equation by 2, and we will get that x equals to 5 over 2. X equals to 5 over 2, so we will substitute x here by 5 over 2. And we will substitute here x by 5 over 2. And in the next step, we will focus on angles APM, angle BPM, this angle BQM, this angle, and angle AQM. On those four angles, we know that the cosine of each one of the four angles of each one of the four angles will be equal to 5 over 2 over 5. So here angle APM angle AQM angle BQM and angle MPB on each of those four angles. We know that cosine of each one of the four angles equals to 5 over 2 over 5. Here this angle is 5 over 2 over 5, cosine of this angle is also 5 over 2 over 5, and here also. So 5 over 2 over 5 is equal to 5 over 5 times 2. 5 over 5 is 1. So cosine of those each four angles equals to 1 over 2, and when the cosine of the angle equals to 1 over 2, it means that the angle itself equals to 60 degrees. So we found out that each one of the four angles is equal to 60 degrees. So I write it down. This angle APM equals to 60 degrees. Angle BPM also equals to 60 degrees. Angle BQM equals to 60 degrees. And angle AQM also equals to 60 degrees. Okay, so in the next step, we will focus on those two right triangles, triangle APB and triangle AQB, and we will prove that those two triangles can go into each other. So we will focus on triangle APB. And triangle AQB. Okay. So why those two triangles can go into each other? First of all, we know that AP equals to AQ equals to 5 units. AP equals to AQ equals to 5 units. We also know that PB equals to BQ equals to 5 units also. PB equals to BQ equals also to 5 units. Here PB equals to BQ equals to 5 units also. And AB equals to itself. AB equals to itself, so AB equals to AB is a common side that belongs to both triangles. So here AB equals to AB is a common side that belongs to both triangles. So we actually proved that those two triangles can go into each other according to side rule. I'll write it down. Triangle APB congruent, this is the sign of congruent, to triangle AQB. According to side rule. Okay, because of the fact that all sides of triangle APB can go into all sides of triangle AQB, those two triangles can go into each other according to side rule. And from the fact that those two triangles can go into each other, we will conclude that they have also the same areas. So the area of triangle APB is equal to the area of triangle AQB. Okay, I will write it here also. The area of triangle APB is equal to the area of triangle AQB. And what is the area of sector APB? The area of sector APB, this sector, will be equal to pi r squared times 60 degrees plus 60 degrees is 100 degrees, 120 degrees over 360 degrees. So, in conclusion, we found out that the area of sector APB equals to pi r squared times 120 degrees, that is 60 plus 60, over 360 degrees. Okay, and r equals to 5 units, so r squared is 5 squared, 5 squared is 25, so in the numerator we have 25 pi over 120 degrees over 360 degrees is 1 over 3, so it is 25 pi over 3 square units. So we actually found out that the area of sector APB is equal to 25 pi over 3 square units. What is the area of sector AQB? The area of sector AQB of this sector AQB will be equal to pi r squared times 120 degrees over 360 degrees. Again, the area of sector AQB equals to pi r squared times 120 degrees over 360 degrees. That is to say r equals to 5, r 5 squared is 25, so in the numerator we have 25 pi, and 120 degrees over 360 degrees is 1 over 3. So we found out that the area of sector AQB also equals to 25 pi over 3. So we can write down that the area of sector AQB, or the area of sector APB, is equal to the area of sector AQB. And it is equal actually to 25 pi over 3 square units. Here we found out that the area of triangle APB is equal to the area of triangle AQB, so we will define the areas of those two triangles as x. So we found out that the area of triangle APB equals to the area of triangle AQB, and both areas are equal to x according to our definition. So I will write it down. We found out that the area of triangle APB is equal to the area of triangle AQB and both areas are equal to x according to our definition. What is the area of segment APB? The area of segment APB, the area of segment APB will be equal to the area of sector AQB minus the area of triangle AQB. The area of sector AQB minus the area of triangle AQB. And we have already found out that the area of sector AQB equals to 25 pi over 3 square units, and the area of triangle AQB equals to x according to our definition. So in conclusion, we found out that the area of segment APB equals to 25 pi over 3 minus x square units. And what is the area of segment AQB? The area of segment AQB, you can see from the drawing that the area of segment AQB will be equal to the area of sector APB minus the area of triangle APB. It is equal to the area of sector APB minus the area of triangle APB. And we have already found out that the area of sector AQB equals to 25 pi over 3 square units, and the area of sector APB equals to x according to our definition. So in conclusion, we found out that the area of segment AQB also equals is 25 pi over 3 minus x exactly as the area of segment APB. Therefore, we will conclude that the area of segment APB is equal to the area of segment AQB. I will write it here, that the area of segment APB is equal to the area of segment AQB. I'll repeat again. We'll conclude that the area of segment APB is equal to the area of segment AQB. And what is the area of the green shape? The area of the green shape the area of this green shape that we are looking for in this question is equal to the area of segment APB plus the area of segment AQB. I'll repeat again. The area of the green shape equals to the area of segment APB plus the area of segment AQB. The area of segment APB plus the area of segment AQB. This is the area of the green shape. But because of the fact that the area of segment APB is equal to the area of segment AQB, it means that we can substitute the area of segment AQB by the area of segment APB because they are equal to each other. So we'll do it now, and we get that the area of the green shape is equal to the area of segment APB plus the area of segment AQB, but because of the fact that the area of segment AQB is equal to the area of segment APB, we will substitute the area of segment AQB by the area of segment APB. So we actually found out that the area of the green shape equals to 2 times the area of segment APB. Okay, so I'll write it here. The area of the green shape, according to what we have already found out, is equal to 2 times the area of segment APB. And what is the value of the area of segment APB? We have already found out that the area of segment APB equals to 25 pi over 3 minus x. When x is equal to either the area of triangle APB or the area of triangle AQB, because of the fact that they are equal to each other, they have the same area, so it doesn't matter at all if we find how the area of triangle APB or the area of triangle AQB. So we will choose the area of triangle APB and we will find out the area of triangle APB. So the area of triangle APB that is equal to X. What is the area of triangle APB? The area of this triangle is equal to the base of the triangle that is actually AB times the height to the base that is PM over 2. I will repeat again. The area of triangle APB equals to the base of the triangle that is AB times the height to the base that is PM over 2. So we will find out the value of AB. First of all, we have already found out that AM equals to MB. AM equals to MB. So if we define AM as H, then MB will be also equal to H because they are equal to each other. So we will focus on this right triangle, triangle AQM. In this right triangle, triangle AQM, sinus 60 degrees is equal to H over 5. I'll repeat again. In the right triangle, triangle AQM, sinus 60 degrees equals to H over 5. Here we will multiply this equation by 5 and we will get that H equals to 5 times sinus 60 degrees, and we know that sinus 60 degrees is square root of 3 over 2. So in conclusion, we found out that H equals to 5 times square root of 3 over 2. But we want to find out the value of AB, and AB equals to H plus H. That is to say, AB equals to 2H, AB equals to 2H. That is to say, it equals to 2 times. H is 5 times square root of 3 over 2. So AB, the value of AB, 2 over 2 is 1. So 2 will get cancelled. AB equals to 5 times square root of 3. We found out that AB equals to 5 times square root of 3 units. So the area X that equals to the area of triangle APB is equal to AB times PM over 2. And we actually found out that AB equals to 5 over 3 times PM equals to 5 over 2, all divided by 2. So here we found out that H equals to 5 times square root of 3 over 2, so I will write it down. And here also H equals to 5 times square root of 3 over 2. So we found out that x equals to the area of triangle APB, that equals to 5 times 5 is 25. So in the numerator we have 25 times square root of 3. And in the denominator we have 2 times 2. 2 times 2 is 4. So x equals to 25 times square root of 3 over 4 square units. Now we can find out the area of the green shape. Because of the fact that the area of the green shape is equal to 2 times the area of segment APB. So it equals to 2 times, and the area of segment ABB equals to 25 pi over 3 minus x, and we've already found out that x is equal to 25 times square root of 3 over 4. So here we will take 25 out of those two expressions as a common factor. So the area of the green shape equals to 2 times. So we took 25 out of those two expressions as a common factor. So what is left from 25 pi over 3 after we took from it 25 as a common factor? What is left? It is actually pi over 3. And what is left from 25 times square root of 3 over 4 after we took from it 25 as a common factor? What is left? It is actually minus square root of 3 over 4. And 2 times 25 is 50. So it is 50 times pi over 3 minus square root of 3 over 4 square units. Okay, the area of the green shape, according to the first method, is equal to 50 times pi over 3 minus square root of 3 over 4 square units. We finished with the first method. In the next step, I will present to you how to find out the area of this green shape according to the second method. So we define the center of this circle as point P, as we did in the first method, and also the center of this circle as point Q. We will define the first intersection point between those two circles as point A, and we will define the second intersection point of those two circles as point B, and we will do the same constructions as we did in the first method. We will join points P and B together by a straight line. I will not repeat on the process, on the things that we do, that we already did in the first method. In the first method, we have already found out that all the line segments here are equal to 5 units. They are the radiuses of those two circles. so I'll not repeat on it. And here we will join points P and Q together by a straight line. We actually, in the first method, we only found out that PQ equals to 5 units because of the fact that it's the center of this circle. So PQ equals to 5 units. You can write here that PQ equals to 5 units. So here, triangle APQ is an equilateral triangle. All of its sides are equal to 5 units. Therefore, it is equilateral triangle, and all the angles of an equilateral triangle are equal to 60 degrees. Likewise, triangle PQB is an equilateral triangle because of the fact that all of its sides are equal to each other, they are equal to 5 units. Therefore, we conclude that all of its sides, all of its angles are equal to 60 degrees also. So here, triangle APQ is congruent to triangle PQB according to side rule. I'll write it down. Triangle APQ congruent to triangle BPQ according to side rule. All the sides of triangle APQ are equal to all the sides of triangle PBQ, and they are equal to 5 units, as you can see from the drawing. From the fact that those two triangles can congruent to each other, we will conclude that they have also the same areas. That is to say, the area of triangle APQ is equal to the area of triangle PBQ. I remind you that the squared brackets is the same for the area, so here it means that the area of triangle APQ is equal to the area of triangle PBQ. So, what is the area of the green shape? The area of the green shape that we are looking for will be equal to the area of triangle APQ plus the area of triangle PBQ plus the area of segment AP plus the area of segment PB plus the area of segment BQ plus the area of segment AQ. I will repeat again. I will repeat again. The area of the green shape equals to the area of triangle APQ plus the area of triangle PPQ plus the area of the four segments, segment AP, segment PB, segment BQ, and segment AQ. Again, the area of triangle APQ plus the area of triangle PPQ plus the area of those four segments is equal to the area of the green shape, the area that we are looking for in this question. So we'll find out but first of all, because of the fact that we have already found out that the area of triangle APQ is equal to the area of triangle PBQ, we can substitute the area of triangle PBQ by the area of triangle APQ. Okay, we'll do it now, and we'll get that the area of the green shape is equal to the area of triangle APQ plus the area of triangle PBQ, but because of the fact that the area of triangle PBQ is equal to the area of triangle APQ, we will substitute the area of triangle PBQ by the area of triangle APQ. So it is plus the area of triangle APQ plus the areas of the four segments AP, PB, BQ, and AQ. Okay? So the area of triangle APQ plus the area of triangle APQ is 2 times the area of triangle APQ. I'll write it down. The area of the green shape will be equal to 2 times the area of triangle APQ plus the area of the four segments AP, PB, segment BQ, and segment AQ. Okay? So, first of all, we have to find out the area of triangle APQ. In order to find out the area of triangle APQ, we will join together points A and B by a straight line. This point is point M. We have already found out that AM is equal to H according to our definition, and H equals to 5 times square root of 3 over 2. We found it in the first method. Here H also equals to 5 times square root of 3 over 2. So the area of triangle APQ will be equal to the base of the triangle, that is PQ, times the height, that is AM, but AM equals to H, over 2. I repeat again, the area of triangle APQ will be equal to the base of the triangle, that is PQ, times the height, that is H, over 2. PQ equals to 5. We have already found out that PQ equals to 5 units. PQ equals to 5, and H equals to 5 times square root of 3 over 2. And all divided by 2. So the area of triangle APQ will be equal to 5 times 5 is 25 times square root of 3, and in the denominator we have 2 times 2 is 4. So in conclusion, we found out that the area of triangle APQ is equal to 25 times square root of 3 over 4 square units. So here, in order to find out the area of the green shape, will be equal to 2 times the area of triangle APB, but we have already found out that the area of triangle APB equals to 25 times square root of 3 over 4. So here we have to find out also the area of segment AP. Okay, so now we will find out the area of segment AP. What is the area of segment AP? The area of this segment AP, will be equal to the area of sector AQP minus the area of triangle AQP. The area of sector AQP, this sector, minus the area of triangle AQP. What is the area of sector AQP? The area of sector AQP equals to pi r squared times 60 degrees over 360 degrees. I write it down. The area of sector AQP equals to pi r squared times 60 degrees over 360 degrees minus the area of triangle AQP. But we have already found out that the area of triangle AQP equals to 25 times square root of 3 over 4 square units. So here r equals to 5. So r squared is 5 squared, and 5 squared is 25. So in the numerator we have 25 pi, and 60 over 360 degrees is 1 over 6. So in the denominator we have 6. So this expression equals to 25 pi over 6 minus 25 times root of 3 over 4 square units. So we actually found out that the area of segment AP is equal to 25 pi over 6 minus 25 times square root of 3 over 4 square units. So in the next step, we'll find out the area of segment PB. What is the area of segment PB? The area of segment PB will be equal to the area of sector PQB minus the area of triangle PQB. The area of sector PQB minus the area of triangle PQB. I'll repeat again. The area of segment PB the area of segment PB equals to the area of sector PQB minus the area of triangle PQB. So what is the area of sector PQB? The area of sector PQB, this sector will be equal to pi r squared times 60 degrees over 360 degrees. Okay, pi r squared times 60 degrees over 360 degrees minus the area of triangle PQB. The area of this triangle PQB. We have already found out that the area of triangle PQB is equal to the area of triangle APQ. Therefore, and we have already found out that the area of triangle PQB equals to 25 times square root of 3 over 4. So the area of segment PB will be equal to pi r squared. R is 5. R squared is 5 squared. 5 squared is 25. So in the numerator we have 25 pi. And in the denominator we have 60 over 60 is 1 over 6. In the denominator we have 6. So this expression equals to 25 pi over 6 minus 25 times square root of 3 over 4. So the area of segment PB is equal to 25 pi over 6 minus 25 times square root of 3 over 4, exactly as the area of segment AP. So we can write here that the area of segment AP equals to the area of segment PB and if we continue to calculate the area of segment QB and the area of segment AQ, we'll get to the same results. That is to say, it will be equal to the area of segment AP. Therefore, actually, we'll conclude that all the areas of all 4 segments are equal to each other, and they are equal to this expression. Therefore, in order to find out the area of segment, the area of the green shape, the area of the green shape will be equal to 2 times the area of triangle APQ plus 4 times the area of segment AP. So I will repeat again. The area of the green shape will be equal to 2 times the area of triangle APQ plus 4 times the area of segment AP. And we have already found out that the area of triangle APQ is equal to 25 times square root of 3 over 4. So 2 times the area of triangle APQ plus 4 times the area of segment AP, and the area of segment AP, we already found out that the area of segment AP equals to 25 pi over 6 plus 25 times square root of 3 over 4. So the area of the green shape equals to this expression. So 2 times 25 is 50. So it is 50 times square root of 3 over 4 plus 4 times 25 is 100. So this expression equals to 100 pi over 6. It's actually here minus. And 4 times minus 25 is minus 100. So this expression equals to minus 100 square root of 3 over 4. So the area of the green shape equals to this expression. Here 50 times square root of 3 over 4 minus 100 times square root of 3 over 4 will be equal to minus 50 times square root of 3 over 4. And this expression 100 pi over 6. We'll divide this expression, both the numerator and the denominator of this expression, by 2, and we will get that 100 over 2 is 50. So in the numerator we have 50 pi. 6 over 2 is 3. So in conclusion, we found out that the area of the green shape, according to the second method, equals to 50 pi over 3 minus 50 times square root of 3 over 4. Here we take 50 out of these two expressions as a common factor, and we get, so we took 50 as a common factor out of this expression. So what is left from 50 pi over 3 after we took from it 50 as a common factor? What is left? It is actually pi over 3. And what is left for minus 50 times square root of 3 over 4 after we took from it 50 as a common factor? What is left? It is actually square root of 3 minus square root of 3 over 4. So in conclusion, we found out that the area of the green shape, according to the second method, is equal to 50 times pi over 3 minus square root of 3 over 4 square units, exactly as we found in the first method. So in the next step, I will summarize the lecture. We found the area of this green shape in 2 different methods. So here I repeat on the question. We have here 2 circles. Each circle is passing from the center of the other circle. The radius of each circle is equal to 5 units, and we want to find out the area of this green shape. So first of all, I presented to you the term sector. Sector, it is actually the area inside the circle that is bounded by 2 radiuses, and the arc that is between those 2 radiuses. So this green shape is sector AOB, and the area of this specific sector is equal to pi r squared times 60 degrees over 360 degrees, but in general the area of any sector is equal to pi r squared times the angle between the 2 radiuses over 360 degrees, when r equals to the radius of the circle. Okay? Then I presented to you the term segment. Segment is the area that is bounded by chord AB and arc AB. So the area that is bounded by the chord and the arc that is attached to it is defined as a segment. So this green shape, the green shape AB, is segment AB, and the area of segment AB equals to the area of sector AOB minus the area of triangle AOB. Okay? And then we actually define the center of this circle as point P, we define the center of this circle as point Q, we define the first intersection point as point A, and of those 2 circles as point A, and we defined the second intersection point of those 2 circles as point B. Then we join together points A and P, P and B, P and Q, Q and A by a straight line. Each of the segments that we created is the radius of one of those circles, therefore it equals to 5 units. For example, BQ is the radius of this circle. Why? Because line segment BQ starts from the center of this circle, that is to say from point Q, and ends at point B, that is the point of this on this circle itself. Therefore, BQ is the radius of this circle, that is to say it equals to 5 units. The same thing is true for the other circles. We'll do the same analysis for the other segments, and we'll find out that the value of each segment, the length of each segment is equal to 5 units. So here we created quadrilateral APBQ, and in quadrilateral APBQ all of its sides are equal to each other. Therefore it is defined as a rhombus. Any quadrilateral that all of its sides are equal to each other and it doesn't have 4 right angles, it must be a rhombus. Okay, here you can see that this angle, for example, equals to 120 degrees, this angle equals to 120 degrees, therefore quadrilateral APBQ doesn't have 4 right angles, therefore it is a rhombus. Quadrilateral APBQ is a rhombus. and quadrilateral APBQ is a rhombus. Then we join together points A and B by a straight line. Line segment AB is the diagonal of rhombus APBQ. Then we join together points P and Q by a straight line. PQ is the second diagonal of rhombus APBQ. And the diagonals of a rhombus has two characteristics. I wrote them here. The characteristics of the diagonals of a rhombus is that, first of all, they are perpendicular to each other. That is to say, diagonal AB is perpendicular to diagonal PQ, and diagonal PQ is perpendicular to diagonal AB. What does it mean? It means that we have here 4 right angles, 1, 2, 3, 4. And the second characteristic of the diagonals of a rhombus is that they bisect each other. That is to say, diagonal AB bisects diagonal PQ. What does it mean? It means that PM equals to MQ. PM equals to MQ. And diagonal PQ bisects diagonal AB. What does it mean? It means that AM equals to MB. So here we have already found out that PQ is the radius of this circle. Why? Because it starts from the center of the circle and ends at point Q, that is a point on the circle itself. Therefore, PQ is defined as the radius of this circle, that is to say it equals to 5 units. From one side, PQ equals to 5 units. But from the other side, PQ also equals to x plus x. So PQ equals to PM plus MB. And if we define PM as x, then PQ equals to PM plus MQ. But PM equals to MQ, because the diagonal AB bisects diagonal PQ. So if PM equals to x, then MQ will be also equal to x. So from the other side, PQ equals to x plus x. So x plus x equals to PQ, but from the other side, PQ equals to 5 units. So from this equation, we will derive that 2x equals to PQ equals to 5. From this equation, we will derive that 2x equals to 5. And we divided this equation by 2, and we got that x equals to 5 over 2. And here, that is to say, PM equals to x equals to 5 over 2, and MQ that equals to x equals also to 5 over 2 units. Okay? Then we actually related to those 4 angles, angle APM, angle BPM, angle BQM, and angle AQM. We focused on those 4 angles, and in those 4 angles, the cosine of each 4 angles, each one of those 4 angles, will be equal to 5 over 2 over 5. Here, 5 over 2 over 5, the cosine of this angle equals to 5 over 2 over 5. So the cosine of each one of the 4 angles is equal to 5 over 2 over 5. 5 over 2 over 5 is 5 over 5 times 2. 5 over 5 is 1. So cosine of each one of the 4 angles is equal to 1 over 2. And if cosine of angle is equal to 1 over 2, it means that the angle itself equals to 60 degrees. So we actually found out that all 4 angles, they are equal to 60 degrees. And then we proved that those 2 triangles can go into each other. That is to say, we proved the triangle APB can go into triangle AQB. Why those 2 triangles can go into each other? First of all, we know that AP equals to AQ equals to 5 units. Again, AP equals to AQ equals to 5 units. PB equals to BQ also equals to 5 units. PB equals to BQ equals to 5 units. And AB equals to itself. It is a common side that belongs to both triangles. So PB equals AB equals to AB is a common side. So we actually found out that triangle APB can go to triangle AQB according to side rule. All sides of triangle APB can go into all the sides of triangle AQB. Therefore, those two triangles can go into each other according to side rule. And because of the fact that those two triangles can go into each other, we will conclude from it that they have also the same areas. So the area of triangle APB is equal to the area of triangle AQB. Okay, so here the area of triangle APB is equal to the area of triangle AQB. So we defined the area of those two triangles as x. Okay, then what is the area of sector APB? The area of sector APB will be equal to pi r squared times 60 degrees plus 60 degrees is 120 degrees, so it is pi r squared times 120 degrees over 360 degrees. The area of sector APB equals to pi r squared times 120 degrees over 360 degrees. Here r equals to 5. So r squared is 5 squared, 5 squared is 25, so in the numerator we have 25 pi, and in the denominator we have 120 degrees over 360 degrees is 1 over 3, so in the denominator we have 3, so this expression equals to 25 pi over 3, that is to say the area of sector APB is equal to 25 pi over 3 square units. Then what is the area of sector AQB? The area of this sector, it is actually will be equal to pi r squared times 120 degrees over 360 degrees. The area of sector AQB equals to pi r squared times 120 degrees over 360 degrees. Again, it is exactly the same expression as this expression, so we found out actually that the area of sector APB is equal to the area of sector AQB, and they are both equals to 25 pi over 3 square units. I will repeat again, the area of sector APB is equal to the area of sector AQB, and they are both equal to 25 pi over 3 square units. And we have already found out that the area of triangle APB is equal to the area of triangle AQB, and they are both equal to x according to our definition. And what is the area of segment APB? The area of this segment APB is equal to the area of sector AQB minus the area of triangle AQB. Again, the area of segment APB is equal to the area of sector AQB minus the area of triangle AQB. And we have already found out that the area of sector AQB equals to 25 pi over 3. Here, the area of sector AQB equals to 25 pi over 3. And the area of triangle AQB is equal to x. Here, the area of triangle AQB equals to x. So in conclusion, we found out that the area of segment APB equals to 25 pi over 3 minus x square units. And what is the area of segment AQB? The area of segment AQB will be equal to the area of sector APB minus the area of triangle APB. The area of segment AQB is equal to the area of sector APB minus the area of triangle APB. And we have already found out that the area of sector AQB is equal to 25 pi over 3, and the area of triangle APB, the area of triangle APB equals to x. Therefore, the area of segment AQB is equal to 25 pi over 3 minus x, exactly as the area of segment APB. That is to say, the area of segment APB is equal to the area of segment AQB. Okay? The area of segment APB is equal to the area of segment AQB. And what is the area of the green shape? The area of the green shape equals to the area of segment APB plus the area of segment AQB. Again, the area of the green shape equals to the area of segment APB plus the area of segment AQB. but because of the fact that the area of segment APB is equal to the area of segment AQB, we can substitute the area of segment AQB by the area of segment APB. Why? Because they are equal to each other. We did it, and we got that the area of the green shape equals to the area of segment APB plus the area of segment APB. That is to say, the area of the green shape equals to 2 times the area of segment APB. So, the area of the green shape equals to 2 times the area of segment APB, and we've already found out that the area of segment APB equals to 25 pi over 3 minus x. And x is either the area of triangle APB or the area of triangle AQB. So we will calculate the area of triangle APB, and here the area of triangle APB will be equal to AB, that is the base, times the height, that is PM, over 2. The area of triangle APB, that is x, equals to the base, that is AB, times the height to the base, that is PM, over 2. So we have to find out the area, the length of side AB. What is the length of AB? If we focus on triangle AMQ, the right triangle AMQ, here sinus 60 degrees equals to h over 5. In the right triangle AMQ, sinus 60 degrees equals to h over 5. Here we multiply this equation by 5, and we got that h equals to 5 times sinus 60 degrees. Sinus 60 degrees is square root of 3 over 2. So we substitute sinus 60 degrees by square root of 3 over 2, and we got that h equals to 5 times square root of 3 over 2. H equals to 5 times square root of 3 over 2, but AB equals to h plus h. So AB equals to 2h. That is to say, AB equals to 2 times h, and h equals to 5 times square root of 3 over 2. Here 2 over 2 is 1, so 2 will get cancelled, and we found out that AB equals to 5 times square root of 3 units. So x, that equals to the area of triangle APB, equals to the base AB times the height, that is PM, over 2. So the base AB is 5 times square root of 3. The height PQ is 5 over 2. 5 over 2 units, all divided by 2. Okay, so here we got that 5 times 5 is 25, so in the numerator we have 25 pi times square root of 3. 2 times 2 is 4, so in the denominator we have 4. So in conclusion, we found out that x, that is actually equals to the area of triangle APB, is equal to 25 pi, and x, that is actually equals to the area of triangle APB, is equal to 25 times square root of 3 over 4 square units. So, and the area of the green shape equals to 2 times the area of segment APB, and the area of segment APB equals to 25 pi over 3 minus x, so it is 2 times this expression. And so the area of the green shape equals to 2 times 25 pi over 3, and we have already found out that x equals to 25 times square root of 3 over 4. So in conclusion, here we took 25 out of these two expressions as a common factor, and we got that the area of the green shape equals to 2 times 25. What is left from 25 pi over 3 after we took from each 25 as a common factor? What is left? It is actually pi over 3. And what is left from minus 25 times square root of 3 over 4 after we took from it 25 as a common factor? What is left? It is actually minus square root of 3 over 4. So, and 2 times 25 is 50. So in conclusion, we found out that the area of the green shape equals to 50 times square root. The area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units. I repeat again, the area of the green shape equals to 50 times pi over 3 minus square root of 3 over 4 square units. Okay, so we finished with the first method. Then I presented to you how to find out the area of the green shape according to the second method. In the second method, we did the same construction as we did in the first method. Here, we actually created here two equilateral triangles. Triangle APQ is an equilateral triangle because of the fact that all of its sides are equal to each other, they are equal to 5 units. The same thing is true about the equilateral triangle PQB, all of its sides are equal to 5 units. So those two equilateral triangle APQ and triangle PBQ can go into each other according to side rule. All the sides of triangle APQ are equal to all the sides of triangle PBQ, and they are equal to 5 units. From the fact that those two triangles can go into each other, we will conclude that they have also the same areas. That is to say, the area of triangle APQ, this triangle, is equal to the area of triangle PBQ, this triangle. Okay? So, what is the area of the green shape? The area of the green shape is equal to the area of the equilateral triangle APQ plus the area of the equilateral triangle PBQ plus the area of segment AP plus the area of segment PB plus the area of segment QB plus the area of segment AQ. I will repeat again. The area of the green shape equals to the area of triangle APQ plus the area of triangle PBQ plus the sum of the areas of segments AP, PB, BQ, and AQ. But because of the fact that the area of triangle APQ is equal to the area of triangle PBQ, here we concluded that the area of triangle APQ is equal to the area of triangle PBQ. That is to say, we can substitute the area of triangle PBQ by the area of triangle APQ. So we did it, and we got that the area of the green shape equals to the area of triangle APQ plus the area of triangle APQ plus the areas of the 4 segments. So the area of triangle APQ plus the area of triangle APQ equals to 2 times the area of triangle APQ. And in order to find out the area of the green shape, we have to add to the areas of those two triangles the areas of the 4 segments, AP, PB, PQ, and AQ. So the area of the green shape equals to 2 times the area of triangle APQ plus the area of the 4 segments. And what is the area of triangle APQ? The area of triangle APQ equals to the base of the triangle that is AB times the height that is PM over 2. Again, the area, actually here, the area of triangle APQ, the area of this triangle APQ, equals to the base of the triangle that is PQ times the height that is H over 2. Okay, PQ equals, so it is PQ times H over 2, that is the area of triangle APQ, but PQ equals to 5 units. We have already found out in the first method that H, that is AM, equals to 5 times square root of 3 over 2. H equals to 5 times square root of 3 over 2, all divided by 2. So in the numerator we have 5 times 5 is 25, 25 times square root of 3. In the denominator we have 2 times 2 is 4. So in conclusion we found out that the area of this equilateral triangle APQ is equal to 25 times square root of 3 over 4 square units. So in conclusion, the area of the green shape equals to 2 times the area of triangle APQ, and 2 times the area of triangle APQ is 2 times 25 times square root of 3 over 4 because of the fact that the area of triangle APQ equals to 25 times square root of 3 over 4. And we have to add to 2 times the area of triangle APQ, the area of the 4 segments. And so we have to find out the area of segment AP. And the area of segment AP here, the area of segment AP will be equal to the area of sector AQP minus the area of triangle AQP. Again, the area of segment AP equals to the area of sector AQP minus the area of triangle AQP. The area of sector AQP equals to pi r squared times 60 degrees over 360 degrees. Pi r squared times 60 degrees over 360 degrees. And we have already found out that the area of triangle AQP equals to 25 times square root of 3 over 4. So here, pi r squared, r is 5, so r squared is 5 squared, 5 squared is 25. And in the numerator we have 25 pi, and in the denominator we have 60 degrees over 360 degrees is 1 over 6, so in the denominator we have 6. So the value of this expression is 25 pi over 6 minus 25 times square root of 3 over 4. So the area of segment AP equals to 25 pi over 6 minus 25 times square root of 3 over 4. Okay, this is the area of segment AP. Then we calculated the area of this segment PB. What is the area of segment PB? The area of segment PB will be equal to the area of sector PQB minus the area of triangle PQB. I'll repeat again. The area of segment PB equals to the area of sector PQB minus the area of triangle PQB. What is the area of segment PQB? The area of segment PQB will be equal to pi r squared times 60 degrees over 360 degrees. Pi r squared times 60 degrees over 360 degrees. What is the area of triangle PQB? We have already found out that the area of triangle PQB is equal to the area of triangle AQP. But the area of triangle AQP is equal to 25 times square root of 3 over 4. Therefore, the area of triangle PQB equals to 25 times square root of 3 over 4. And here, pi r squared, r is 5, so r squared is 25, so in the numerator we have 25 pi, in the denominator we have 60 over 360 is 1 over 6, so in the denominator we have 6. So in conclusion, we found out that the area of segment PB equals to 25 pi over 6 minus 25 times square root of 3 over 4, exactly as segment AP. That is to say, the area of segment AP equals to the area of segment PB. And if we continue to calculate the area of segment BQ and the area of segment AQ, we will find out that the area of those two segments AQ and BQ is equal to the area of segment AP. Therefore, the area of the green shape. So, in conclusion, we can say that the areas of all 4 segments are equal to each other. Therefore, the area of the green shape will be equal to 2 times the area of triangle APQ plus 4 times the area of segment AP. Okay? And here, the area of triangle APQ is 25 times square root of 3 over 4. So we will multiply it by 2 plus 4 times the area of segment AP. We have already found out that the area of segment AP equals to 25 pi over 6 minus 25 times square root of 3 over 4. So the area of the green shape equals to this expression. Here 2 times 25 is 50, so this expression equals to 50 times square root of 3 over 4 plus this expression 4 times 25 is 100, so the value of this expression is 100 pi over 6, and 4 times minus 25 times square root of 3 over 4 is equals to minus 100 square root of 3 over 4. So here 50 times square root of 3 over 4 minus 100 times square root of 3 over 4 equals to minus 50 square root of 3 over 4. It equals to minus 50 square root of 3 over 4. And here we have the expression 100 pi over 6. If we divide both the numerator and the denominator by 2, we'll get that 100 over 2 is 50 and 6 over 2 is 3. So in conclusion, this expression equals to 50 pi over 3. So in conclusion, the area of the green shape equals to 50 pi over 3 minus 50 times square root of 3 over 4. Here we took 50 out of those two expressions as a common factor, and what is left from 50 pi over 3 after we took from it 50 as a common factor, what is left is actually pi over 3, and what is left from minus 50 times square root of 3 over 4 after we took from it 50 as a common factor, what is left, it is actually square root of 3 over 4. So in conclusion, we found out that the area of the green shape according to the second method is also equal to 50 times pi over 3 minus square root of 3 over 4, exactly as we found in the first method. Okay, thank you very much.